So let me introduce our next speaker. Our next speaker, Theo, is a serial entrepreneur, investor, and technologist. He has founded 6 companies and served as the founding engineer for 2 product lines. Remember that we have our Slido application, so if you have any question and answer, please register over there. So please help me with a really warm welcome to Theo Schlossnagle.
Hello, hello. If you're surprised to see me, I'm surprised to be here. I'm giving another talk later, but this talk is about software abstraction. So sort of a unique take on software abstraction, kind of dissect what it means. I'm sure that all of you have dealt with software abstraction because you cannot not deal with software abstraction. What I hope to do is have you think a little bit differently about how software is abstracted compared to perhaps how you were taught it was abstracted in school. So briefly, I'm Theo Schlossnagle. I founded a couple of different companies. I'm a very active member of the ACM. Do a lot of open source programming, a lot of software out there, about 100 different projects that I've contributed to. And I pretend to farm, so that's different. Okay, so what is abstraction, right? So the boundaries between different software layers of the stack and the hardware layers of the stack, basically so that you don't have to think about how electrons move through transistors when you're writing JavaScript, right? It's a little bit of a cognitive load to have to think about how computers work while you're trying to program. So basically, we define these layers of abstraction so that we can do our jobs. So this probably looks somewhat similar to any sort of classic abstraction model from like a computer science program. And I've added the software-hardware boundary there because that's, in my opinion, where those things flip over. If you talk to an electrical engineer, they'd probably move that down 1 or 2 levels. But typical software engineers, once you hit the instruction set architecture of a system, like if you're programming on an Apple M1 and it's ARM-based, or you're programming on an Intel box and it's x86, 64, those instruction set architectures, and then some of the machine-dependent things that happen, like the memory models and things like that, start to take effect. And below that, amazingly, there's a lot of code that teaches your processor how to do things differently. So a lot of people think that those instruction set architectures go into hardware and they're just run on hardware, but they actually go into hardware and they run on microarchitectures. So if anybody's ever seen like a microcode firmware update for their CPU to change how instructions are run, that's because there's software in your hardware. So this is the classic abstraction boundary, right? And the reason that this exists, again, is so that you can do your job. But when you're writing a front-end application, you're writing a database or something like that, and you're interacting with your IDE, and maybe you're using some data structures or algorithms, you probably don't want to be thinking about the semantics of how that programming language is implemented. You don't want to think about, like, what was the JavaScript, V8 engine, or what is my Java compiler, JDK, whatever, what is it thinking right now when I type this in? How is it transitioning my class into something else, into some sort of lower level model that's not a machine model, but it's more of a memory layout model that then gets transitioned down into machine code that then gets put onto an x86, 64, or an ARM processor. Typically, those are your 2 choices. And then gets executed in microarchitecture, and then hardware, and then there's actual, electrons floating around in transistors. You don't need to think about how your transistors were PNP doped or anything like that, right? Because if you had to think about that, your eyes would glaze over, and you would never do any part of your job. So this is the classic model for software abstraction. But I want to say that people don't tend to think about this. This sort of model is fixed. You don't get any choices in this model. It's very rare that you can write programming languages that affect microarchitecture. There are jobs out there that are like that, but they're very, very uncommon. So the first problem with abstraction is that typically when we're thinking about abstraction boundaries, the number of dimensions that you can abstract tend to be about 1. Right? You get basically one choice on where to draw that boundary. You can't have a fence that between two properties that is in multiple places at once. It's usually you've decided a property line, and on this side of the property is one team, and on the other side of the property is another team, and they write different code, they have different problems, and things like that. But the problem is that typically where you put that fence is you have an option to put it in one space to divide a thing into two groups, but it's not always obvious what that division should look like, right? Is it a division between available hireable skills, right? So I have a problem set and I want to solve some of it with a database and some of it with code, but database engineers are really hard to find now and coders are really easy to find, so maybe I should draw the line so that I can hire people easier. Maybe I'm storing private data. Maybe I have all sorts of really interesting GDPR requirements. So I want to put the boundary on that fence to make my security, my compliance, my liability to government easier to manifest. So I put stuff that gets me in trouble legally on this side and stuff where I don't have to care about it on this side, and it makes the thought processes of building those systems easier. So the team that builds on that side of the fence has to consider and be fluent with GDPR, and the one on the other side of the fence, they don't have to worry about that. And then you have other ones. Resources is efficiency. So I have a system where I'm in the cloud and I have certain things like compute, I have memory, I have storage, and they all cost different amounts. Do I draw my lines there so that I can leverage each of those different types of resources and their cost efficiencies differently, right? Availability, this is one of my favorites because my life is spent doing highly available systems. And it also falls in the line of safety and correctness. If you have a system that needs to be up 99.999% of the time, ideally you want that system to be as small as possible, right? So you have, say, 50 APIs that you provide to your customer base, and someone comes in and says they need to be available 5 nines. The first question is really all of them? I hope not. Maybe it's these 4 that need to be available all the time, and all of these others don't. And if I can draw an abstraction boundary there, then I can invest the money to make the small set available while saving a lot of money and time and effort by making the rest of it a little less available. So as you can see, you have all of these different things that you could divide, these different spaces, these different dimensions where you can divide, but you really can't choose all 5 of them. You end up choosing one. Sometimes you'll choose one, and within that one, you'll choose another one. So this is the first problem that we have with abstraction, is that we have some difficult choices to make. So here's a sort of an example of, so I spend my life writing a time series database. And it stores all sorts of data. We take telemetry data in, trillions of measurements off of systems, and we store it in a database, and we allow people to ask questions like, give me a mathematical model of trend lines over the last 12 months for these 10,000 data points. So there's a lot of work that happens in the database, and it would seem pretty simple. First rule of databases is don't write your own, use someone else's, because they already did that work. But it turns out that some of the things that we want to do here with ingestion and with reporting aren't solved well with traditional databases. I'll get into a little bit of that why later, but what we'll see is that if you use a traditional API for going into a database, there are certain jobs or certain feature sets of that database that become really hard to implement without violating those layer boundaries. You kind of have to, I mean, I'm sure people who have used an API from another team, say a microservice, you kind of have two choices. You either kind of go around them, or you open a ticket and say, hey, your API isn't sufficient. I need something new. I need a different way to access this metadata or this system. And those end up being abstraction violations or leaky abstractions that sort of expose the data model, that make it ugly. And I think that a lot of people who look at systems and want them to be elegant and beautiful, they try to build these abstraction layers and make sure that there's no leaking, right? You don't need to know the data structures or the data models that are behind it. And that seems great, but after a couple of months of work with that system, suddenly like all of the goods are out, right? You kind of know how it's built on the inside because it didn't work right. So you end up violating you either leak the abstraction or you violate the boundary. So what's another problem with abstractions? So this is the most common problem that I see with abstractions, is that people abstract too soon. So you have a core problem that you're trying to solve. I don't know, how many people here have written a library or a framework or something like that that gets reused in the organization? So a couple hands. So one problem that we see a lot in computer science is that someone is building something and they go, oh, this will be generally useful, so I'm going to make it useful for everyone. And the problem is that you're the only consumer at that point. There's like one stakeholder, and it's your idea of who that stakeholder is. So you're trying to arbitrate your techniques and resources and access to data and all that kind of stuff by building an API abstraction. And you're trying to deliver certain things: performance, scalability, availability, all of those things. But you're also delivering it for an audience. And I think that the lesson that's a really hard lesson to learn is that a lot of people think about their APIs in terms of, how do I best build this API to deliver the availability requirements or the performance requirements? But at the end of the day, the hardest thing to satisfy is all the stakeholders. You actually have consumers of this API. And until you have more than 2 or 3 consumers, I guarantee you build that API wrong. So ideally, you want to build a system and not abstract that boundary until you have multiple stakeholders that help define where that boundary should be, because you're going to build it in the wrong place otherwise. So the third problem, and this is sort of like the old engineer with the beard. My beard's shorter now, but I still get a little grumpy when people have problems with their systems and they don't understand why. They have no idea why, whether or not they're programming in C++ and they're using some sort of standard template library and the hash table is slow, and they're just like, hash tables are supposed to be fast. And you're like, what are you talking about? You're in a different memory model. You're on a NUMA system with processors that have access to different memory buses, and you've exceeded the size of the memory in one NUMA node. So like, you're going to have to cross-fetch across the bus. It's going to be super expensive. And then their brain explodes, and they're like, I just wanted to use a hash table. Why is this hard? So the problem with abstractions is that they allow you to not think about the consequences of your actions, which is great until those consequences are bad. And we see this all of the time, particularly with databases, large-scale applications, things with availability requirements. You don't understand why a certain API is broken into 3 pieces, and you're like, I never want to use those 3 pieces separately. I always want to just do them once. Why don't I just do them once? And the answer is, behind the scenes, is that they have very different availability requirements and performance guarantees that they can make, and somebody somewhere can use only 1 or 2 and not all 3 of those APIs to be able to build a system and not suffer the consequences of kind of their conjunction. So I see this as a problem. This is sort of like where my career lives, is that I come in and try to fix broken shit. And usually, when you talk to teams, if you've got a team of C++ developers or C# developers or Scala developers or whatever, if you have a problem in that language, you don't need any help. That's your domain expertise, right? But when you start building more complex systems and they cross through these layer boundaries of abstractions, when things break, it's very hard to reason about them when you don't know all of it. And of course, they're abstracted because it hurts to know all of it. It's very, very expensive mentally to like have all of these different models in your brain. So this actually results, it's a double-edged sword, right? So the problem with the abstraction is also the benefit with the abstraction. The abstraction allows you to think only in Scala. You don't have to think in microcode. You don't have to think in memory architectures. You don't have to think in latencies, anything like that. However, you're not thinking that way, and when things go wrong, sometimes those problems become intractable. And you end up having to have different expertise in an organization who can sort of violently violate those abstraction boundaries to solve problems. So real life, abstractions clearly are a win because everyone can do their job. They're clearly a loss because no one can do their job well. And it's most often a combination of both of those things. So a really quick case study in our database, which is a great case study because most of you probably don't use it, so it's a little abstract. So it's a highly scalable, distributed, share-nothing database that stores petabytes of time series data to do trending and anomaly detection and all sorts of stuff like that. Primarily written in C and C++ because it needs to be fast. It's not written in Rust because when we wrote it, Rust was not a thing, but it would be written in Rust if we were writing that today. There's a little bit of assembly in there as well. It's very important that the system is correct. So there are two things about that correctness that are very important to us. One of them is it's a distributed system, and distributed systems are very hard. So if you try to solve all of your distributed systems problems in C and assembly, you now have multiple problems that are very hard. So you want strong, easily provably correct data structures. We use CRDTs, which are conflict-free replicated data types. And then the math, it's a database that does math, so it'd be pretty bad if the math was wrong. Getting a mathematician to come in and validate something that's written in C or Fortran is something that only happened in the 70s. That's not a thing anymore. So that's a problem that needs to be solved. The other is the scalability and performance have to do, there's a lot of kind of advanced programming techniques that have to go into that. We use RocksDB from Facebook, we use LMDB from Simus, both open source. And then we use some techniques around resource pools to be able to orchestrate scalability and performance. And then we have this accessibility requirement. So it's accessible over HTTP, but one of the other things is that we want programmers to be able to interact with the database in a low-risk way. And asking a programmer to coast into your database and write assembly is a big F you. You don't want to do that. So that's sort of like the landscape. So one of the things that we did early on, knowing that we would never be able to draw those boundaries in the right place in the first place, is that we built a system that's an event-driven, multi-threaded library that's written in C, but it has Lua built into it. I don't know if anybody's familiar with Lua. It looks like JavaScript, but it has sane language semantics. It's a functional language, sort of acts object-oriented if you want it to. It's very, very simple language. It has an elegant embedding model, and LuaJIT is kind of a re-implementation of that language that does real-time JITting. It's incredibly fast. So we built, all of this stuff is open source. We have a library called libmtev. Probably nobody here writes in C or C++, but it's a C library for doing high-performance distributed system work. And then because people don't write C very well, specifically mathematicians don't write C very well, we wanted to extend it in Lua. But the reason that we chose Lua and not something more popular like Java or JavaScript or Scala or anything like that, Ruby was asked for when we were doing that because it would make development really easy, is because the way LuaJIT is embedded in the system affords us the opportunity to violate boundaries willy-nilly. It's just very easy for us to get in and out of C, assembly, C++, and Lua. So anytime we write something in Lua and we decide that we like it a lot and it works really well and we're not going to change it, we can shift that into C++ with almost no effort. So moving the boundaries around is really easy. So if you haven't used Lua, it's if you do gaming, it's actually the most popular embedded gaming language in the world. Adobe Photoshop, for example, all the scripting internally is done in Lua. So we're not the only people who kind of realize the elegance and beauty of this. And it's not just that it's a nice language, it's a fine language. It's that for people who kind of don't know whether they want to write in C or C++, or a high-level dynamic language a la JavaScript, it allows you to delay the decision of where to do those boundaries because they're so easy to move around. Database abstractions. So I guess the sum of this is that database abstractions are mistakes layered on mistakes layered on mistakes. That is universally true of all databases. So the real problem is that when you have a high-performance database, you want data to come in really fast. But of course, you want to be able to answer questions, usually point-in-time questions, but you also want sort of reporting questions to come out of it. You want sort of everything. The difference between a time series database and other databases is that if your MySQL database, your Postgres database goes down from your website, usually there's no data coming in, and users are very unhappy. But when the database comes back up, you don't have a backlog of data. You have a backlog of desire from your users. But in a time series database, all of the data is actually being generated by machines around the world. And that data is there waiting. So for every minute that you're down, that's another minute of data that you have to catch up on. It's not like the data goes away. So one of the most important things in this type of database is that you always need to be able to accept data. So you need near 100% availability on ingestion of data. Reporting of data, of course you want it to be available, but it's usually a user that's asking for the report, and then they just get mad and come back later and ask for the report again. But the data doesn't get mad, it's an avalanche. So it's really impossible in most database systems to solve these sort of multifaceted problems without layer violations. I mean, to the point where in our database system, we use LMDB, which is a B+ tree style memory map database. And we have portions of code that just like walk through literal pages, don't even use the database. They just go looking for data in there. You dissect the trees, don't use locks, because we know that it's okay if we get sort of wrong data at certain times. Things for like planning, analytics and statistics on databases and things like that. Getting the size of a database, for example. Usually getting the size of a database is really expensive. So you can cheat, you can go around. But these layer violations happen sort of all over the place. And another one that's really interesting is resource boundaries. So one of the things that I think people don't think about a lot is that they think of resource boundaries and performance characteristics around things like monoliths or components and microservice architectures. But from like a universal scalability law, like in practice, those constraints and those scalability limitations tend to manifest around actual resources, right? So they manifest around CPU memory disk, L2 cache network, things like that, that are actually limited. And when you have a microservice that uses all of these different things, you are always underusing some of them, you're always overusing some of them. So your bottleneck tends to move into different places. So one of the things that was really interesting that took years to develop on our side was that we sort of changed the way we schedule work, and instead of scheduling work by workload or task, we would cut jobs up based on what resources they use. So if we have a job that scans and sorts something versus counts things, we would split up those things based on how hot they were on things like L2 cache or network or CPU. And that way we could optimize each portion of the job. So it was a really interesting and kind of novel way to set a boundary for abstraction. But it definitely required programmers to think, hey, I have this job and it does lots of different things. How do I want to break it up? Do I want to break it up on expertise? Do I want to break it up on domain of knowledge? Do I want to break it up on resource boundaries? And it turns out when I want to go fast, you have to break it up by resource boundaries. So let's see what the 10 minutes. So there are some concrete lessons that I hope that you can take away from abstraction work. And I think the most important one is that legacy abstraction model from like software and data structures and programming languages and things like that. That is, it's immutable, it exists, you can more or less ignore it, but you have a lot of decisions to make on your abstractions, especially since microservice architectures are so much more popular today. So the first thing is that abstractions are required. So you can be angry at abstractions all you want. I get angry at abstractions a lot, but it should never, you should never tilt at eliminating these abstractions. They're critically important to make teams functional. The idea of onboarding a new engineer without any abstractions in place sounds like a multi-month exercise before they're productive. It doesn't make sense. The next one is that you should very, very carefully consider what dimensions you're going to be breaking up your abstractions on. Because a lot of times people think of breaking up abstractions based on data domain. So a classic one is I have like a login service and it has user credentials in it and identities, and I'm going to put a boundary around that so that the team that deals with user information and authentication only has to think about that and provide services to everyone. There's nothing wrong with that, but that's a very intentional boundary around data domain and expertise. And maybe that's not necessary, right? Maybe there are things in that system that are require very high availability, like authentication. And there's other things that don't require high availability, like recalling people's mailing addresses or phone numbers, right? That's not something that needs to be up 6 nines or 7 nines. 99% is enough there. So by putting that in one bubble, you kind of have to provide the highest level of availability to all of that domain. I think the most popular one, though, or the most effective one that I've seen, is segregation or boundary definitions around compliance. So specifically things like when GDPR landed in the US, we have the PII stuff for PCI compliance. I think that's more than just the US. There are all sorts of things where the obligations of a company legally apply to certain pieces of data and not other pieces of data. And if you can draw an abstraction boundary between the two of those, then you end up saving a lot of money at the end of the day, right? So securing a system and making sure the data is not misused can be very, very expensive. You have to regulate access to all employees. You have to know who is accessing when and what, and audit trails, you have to store those. You may need third-party audits to come in and look at it. And if you have everything in one bucket, you have to pay for all of that to be audited. And if you take just the things that have compliance requirements and you put them in, you put an abstraction boundary around those, then everything that lives outside of that requires less investment. The third lesson is, I think, learned through painful experience, is that when you are creating a boundary, you have to understand that when you're the only stakeholder, it's very hard to build a product for an audience of people when you're the only customer in the beginning. You end up building it for an audience of one. And you are biased. You have specific ideas about how that data will be used, how that API will be used, how the abstraction should be used. It's very important to have as many stakeholders as possible. So there's two ways to do this. One I hate, and the other one I love, because I like to bust into the room like the Kool-Aid man and just do stuff. One way is that you can create a board or a committee that kind of identifies who would the stakeholders be. This is really classic in enterprises. You say, I'm going to be building this thing. We think it's going to have an abstraction boundary here. These are the potential customers. Then you go out, you find your stakeholders, you build a committee, and they actually aren't using it yet. This is the big problem here. It's that they're all thinking about how they would use it, and then they become their own imaginary stakeholders. And then they help define this boundary. And then they become real stakeholders later and they go, yeah, I didn't do a very good job of that. The better way is to just do it and put the boundary wherever you want. And then when you're building it again, you cut and paste it and you do whatever you want, put the boundary in a different place. And then when you do it a third time, you go, hey, I see a trend here. Maybe I should take these things and put them into one thing. Now that I have real stakeholders that are building applications and building, value off of these things, now that I have multiple stakeholders, multiple consumers of an API, multiple people interfacing with a boundary, an abstraction boundary, then you start to think about how do I build this boundary so it makes sense for all of these stakeholders. So I like to so never build an API without a real consumer is the lesson here. And your tests do not count at all. They are not a consumer. They are, in the best case, something valuable. In the worst case, a masturbatory effort. The fourth lesson is that leaky abstractions happen, right? So inevitably, someone is going to want. So you have an API abstraction that says, I would like to get a user by their last name, right? I'm going to look up a user by their last name. And it turns out that it's very, very slow. So someone ends up requesting users by ID and then filtering by last name, and it's actually faster. Right? A lot of times that's like a reverse engineered leaky abstraction. What they found out was that your API didn't have an index or didn't have an optimization path for one thing. They intuited by interacting with the service and observing latencies that you have some data structure or some pattern that's faster another way, and you've leaked effectively the abstraction there, right? Those things are inevitable. So sometimes they're incredibly overt, like you expose the members of a class or something like that, expose the members of a data structure internally, and allow people to access it. So they're not good, but you should make sure that they're really intentional. Right? There shouldn't be a reason to leak an abstraction unless you're really good friends with who you're leaking it to, I guess is the right way to say it. And the fifth one is that layer violations happen, right? They happen all the time. And I'm really unapologetic about this. I think of layer abstraction boundaries more as guidelines, right? So they aren't fixed, right? You can always go around someone's API. You do it at your own risk. But these things happen all the time. If you go look in the Linux kernel code, there's some gross stuff that happens in there. If you go look in any of your enterprise applications, there's probably some really gross stuff that happens in there. And even people who build really tight boundaries around their products and services, their components, inside their component, they end up violating someone else's layer boundary below them when they include a component. So I think that these things cost, right? But you have to accept it and figure out whether or not it's valuable, right? There should be good return on investment for violating a boundary. And the most common case for this is debugging, Like when you debug something, when something is broken, all of those layers and all of those boundaries, they all become really irrelevant. Because your job is to fix the problem, not figure out which side of the fence to walk on. Right? So you need to be able to violate these things during debugging. And that's it on my, yep, 1 minute. Questions and answers. Yeah, no, we can do questions. Yeah.
Thank you, Theo, for your nice talk. So I wonder, guys, if you register your questions here. Let me see if there is any.
How do you handle changing abstraction boundaries when you already have users? Do you support all previous versions? This really depends on, I think this is one of the reasons why having sort of service level agreements and commitments, deprecation policies. If anybody's ever used Java, you know that they don't always support all previous versions of their APIs. They do get phased out. It's important to be very far ahead of this because it's nothing worse than deprecating something and then deprecating it a year after you wanted to and then supporting it 2 years after that. It might as well become a permanent fixture. So what I typically do when we're changing application boundaries is if it is there's two types. There's the breaking change where the application boundary before was sort of fundamentally in the wrong place or in a dangerous place, right? If you need to change the boundary for a justifiable reason, for example, compliance, like the answer is too bad, right? That data shouldn't be over there because we're going to get in trouble for it being over there. It needs to be over here. That's a change and people are going to break and they have to cope with it. You'll see that with third-party services quite often where the API just changes and you're like, what the hell? And then you go fix your stuff. That happens internally too. If you want to be more gentle to that, you add a new API boundary and then you try to coerce people. Ideally, you add a new API boundary and you implement the old API boundary in the new one, and then it may be a little slower, so it actually really encourages people to switch over. But a lot of times you can re-implement an existing boundary layer on top of the new one.
Great. Theo, just give me 5 seconds. In the name of the craft organizer, we will like to appreciate you and thank you for your wonderful talk at Craft. Could you please help me with an applause to him?
Thank you.